Okay, so Junior Roberts here with realjuniorroberts.com. In this video, we're going to be looking at a question on radioactivity, right? So let's get started with it. So it says here, an investor is interested in a nuclear power station. He has the option of using natural or artificial radioactive decay processes to obtain energy. In helping him to decide, he consults an engineer who compares the energy obtained from the following two nuclear reactions. Right, and here we have our two nuclear reactions. We have one that undergoes a natural process and one that undergoes an artificial process. All right, now we saw where we have bismuth decaying to form thallium and helium plus some amount of energy. That's for the natural process, and for the artificial process, we have uranium being struck by a neutron, right, to form xenon and strontium, and three other neutrons plus energy, right? And here we have a table, right, of some elements, right, and their respective atomic mass in atomic mass unit, which is represented by the unit U. So let's see what we have to do with this question. So first thing they say we need to do is to calculate the number of neutrons in bismuth. Right, so we need to calculate the number of neutrons in bismuth. So to do that, we're going to look back at our equation here. Right, so here's our bismuth element, and we want to know the number of neutrons. Right, so we're going to take this information here and write it below. Right, so we'll have bismuth. Right, bismuth. This was 83. And this here is 212, right? Now we know from our atomic notation, right? Let us say this is our element, right? The number here, let us say this is Z, right? And let us say this is A, right? We know that Z is what we know as our atomic number, right? Or number of protons, right? And A is what we refer to as our mass number, right, or number of protons plus neutrons, right? And we can apply the expression in which we say that A is equal to Z plus N, right? In which A is our mass number, Z is our atomic number or number of protons, and N is the number of neutrons, right? So we're going to consider in our case A is equal to Z plus N. Right, and we're interested in finding N, which is the number of neutrons. So we can rearrange this equation to make N the subject, and we're going to get that N is equal to the mass number minus the atomic number. Right, so in doing so, our mass number is at the top, so it's 212. So we're going to say 212, right, minus the atomic number. In this case, that's 83. So we say 212 minus 83, and we can pull on the surface of our calculator, right? And we'll simply say 212 minus 83, right? And we'll get an answer of 129, right? So therefore, bismuth contains 129 neutrons, right? Which is what they wanted us to find here. Now it says now to determine the atomic mass number of xenon. Right, so again, we're going to look at our element, right? So this is our element xenon, right? But notice that we're not given the complete atomic notation, so the mass number is left out, right? So the mass number is left out, but we can consider this equation. So we can look at the atomic number of our reactants, which are our neutron and uranium, as well as the mass number, right? And the atomic number, the total atomic number must equal to the total atomic number on this side. Similarly, the total mass number must equal to the total mass number on this side. So since we're interested in the mass number of xenon, which is here, we can consider that the mass number of our products is 235 plus 1, so that's 236. and that must be equal to the total atomic number on this side. Right? So we're going to say A, which is our unknown for xenon, plus 90 here, plus 3 neutrons. So we're going to say 3 times 1, which is 3. So when we add all this up, we're going to get, right? So if we go to the side here, right, we're going to get 236, right, is equal to A plus 90 plus 3 is 93. So we can make A the subject, and when we do so, we're going to get that A is equal to 236 minus 93, which is equal to, we just get to our calculator, right, and we say 236 minus 93, right, and we get 143. So therefore, the mass number of xenon, right, would be 143, right, and that would be our answer there, right. So we would have just found the atomic mass number of xenon as 143. Now, the next question wants us to calculate the energy release in each nuclear reaction and the ratio of the larger to the smaller, and then we're to deduce the recommendation that the engineer will give to the investor. Right, so for this one, we're going to consider Einstein's energy mass equivalence equation, which states that E, which is energy released, is equal to the change in mass, delta M, times the speed of light squared. So we get E is equal to delta M C squared. Now, in order for us to do this, right, let us first consider that we're going to do it for both cases. So we're going to consider the natural reaction, right, and then we're going to also consider the artificial reaction. So let's scroll back up to get some information, right? So we have bismuth decaying to form thallium, right, and a helium atom plus energy, right? So we're going to consider the mass of our reactants and the mass of our products to determine our mass defect, which is delta M, right? So we're going to rewrite this expression here, right? So we'll write our nuclear equation, right? And it's given by, we have bismuth, right? 21283, right? Decaying to form thallium, 208 and 81, plus a helium atom, right, plus energy, right? So again, what we'll be considering is the mass of our, in this case, a single reactant, and the mass of our product in order for us to find our mass defect, which is delta M. Right, so we're going to say, first of all, that delta M is equal to the mass of the reactants. So we're going to say mass of the reactants minus the mass of the products. Right, in this case, our reactant is bismuth, so we're going to look back at our table to find the mass of bismuth in atomic mass unit. So that's given us for bismuth, that's 211.99127. So we say 211.99127, and that will be taken, and we will subtract from that the mass of the products, which is thallium and helium. So we're going to look back at our table. So the mass of thallium, right, is given as 207.98201. So 207.98201, right, just confirm that, right, minus the mass of the helium atom, which is given here as 4.00260. So we have 4.00260, right? So in this case now, we just simply do our calculation. So we're going to grab our calculator, right, and we're going to say 211.99127 minus bracket, and we say 207 to 207.98201 minus, well, it should be plus, sorry, it should be plus right there. So 207.98201 201 plus 4.00260, close bracket, right? And then we say equal, and we get a mass defect of 0.00666. So in other words, we get 6.6 times 10 to the minus 3, right? And this would be atomic mass unit, right? Now, we need to first, before we can actually apply our formula, we need to convert this from atomic mass unit to kilograms, right? So we're going to do so by just multiplying this by the value for the atomic mass unit, which is given here. All right, it's given here as U is equal to 1.66 times 10 to the minus 27 kilograms, right? So we're going to say, we're going to take our mass in atomic mass unit, and we're going to say 6.6 times 10 to the minus 3 multiplied by 1.66 times 10 to the minus 27 kilograms. Right, and we'll do so, right, we're going to get, so we take our calculator and we say 6.6 times 10 to the minus 3. Right, so we say 6.6 expressed to the minus 3 equal multiplied by 1.66 expressed to the minus 27. Right, and we get 1.0956 times 10 to the minus 29. So we say 1.0956 times 10 to the minus 29, and this would be kilogram. So now we can consider our equation, right? And we're going to say now that E, which is the energy released, is equal to delta mc squared, right? So we're going to say delta m is 1.0956 times 10 to the minus 29 multiplied by the speed of light squared, which is 3 times 10 to the 8 squared. Right, and this is meter per second, and this is kilograms. Right, so we can squeeze this in meter per second, and this is kilogram. Right, so now when we get our calculator, right, we have our value right here, then we're going to say now multiply by 3 expressed to the 8 squared. Right, and then we say equal, right, and in this case we get 9.8604 times 10 to the minus 13, and in this case it's going to be joule since we're dealing with energy, right? And this is for the natural process. So we're going to also attempt for the artificial and see what we get. So this is artificial, right? And the first thing we're going to do again is we're going to write our equation, right, which is 1 neutron, right, plus uranium-235, right, 92, to form xenon, right, which is 54, and we calculated this before, which was 146. Let's just double check, so 143, so we get 143, right, plus strontium, which is 90 and 38, plus 3 neutrons, right? So now, again, we need to find delta M, right? And we say now that delta M is mass of the reactants. In this case, we have 2 reactants minus the mass of our products. So now, we can now write that the mass of our reactants is our neutron and the uranium. So we're going to find these masses in atomic mass units. So we're going to go back to our table, right? And we'll find the neutron, and we'll find, well, let's write for neutron, that's 1.00867. So we have 1.00867. That's atomic mass unit. So we can say U plus the mass of uranium. Right, so uranium is 235.04393. So 235.04393. So 04393. And that's our reactants minus the mass of our products. We're going to put it below here. All right, so our products in this case are xenon and strontium, right, and 3 neutrons. So for xenon, right, we have 142.93489. Right, so we're going to write that down. So for strontium, for xenon, it's 142.93489 in a bracket plus the mass of strontium. So let's go back. So strontium is 89.90730. So 89.907.3, right? Plus, we have to consider the mass of 3 neutrons, right? So mass of 1 neutron is this, so we can just simply write 3 times this. So if we take our calculator, right, and we say 3 times 1.00867, right, we get 3.0. So we're going to write it then. Let's get some space here. So we're going to write it as plus 3.02601 in a bracket, and this is all in atomic mass units. So again, we're going to get to our calculator, right, and we're going to say now that delta M is equal. So taking our calculator, right, we'll simply say open bracket 1.00867 plus 235.04393 close bracket minus open bracket 142.93489 plus 89.9073 plus 3.02601 close bracket, and then we say equal, and we get in this case 0.1844, and this is U. And again, we convert from atomic mass unit to mass unit by multiplying this by the value for the atomic mass unit, which is 1.66 times 10 to the minus 27. So we can write then that delta M will be equal to 0.1844 times 10, times 1.66 times 10 to the minus 27. So when we do this now, we say that multiplied by 1.66 expressed to the minus 27, and we get 3.06104. So we can write it as 3.06104 times 10 to the minus 28. In this case, is going to be kilograms, right? So this would be kilograms here. So we get kilograms. And again, we're trying to find the energy. So we're going to say now that E is equal to delta mc squared. All right, so delta M now is 3.06104 times 10 to the minus 28 multiplied by the speed of light squared, which is 3 times 10 to the 8 meter per second, and this is squared. So now, taking our calculator again, right, we have our value right here, which is for the mass, the change in mass or the mass defect. So we're going to multiply that number by 3 expressed to the 8 squared. And when we do so, we get 2.754,936 times 10 to the minus 11, so times 10 to the minus 11 joules, right? So we would have just calculated the energy in each case, right? So now they also wanted us to talk about the ratio, right? So the ratio of the smaller to the larger. So let's look back at our values, right? So in this case, right, for the natural, we have 9.8604 times 10 to the minus 13, right? And for the artificial, now we have 2.754,936 times 10 to the minus 11, right? So in this case, the natural would produce a smaller energy. So what we need to do is to divide the larger by the smaller. So we take our calculator, right, and we simply say Since the artificial is the larger, produces the larger amount of energy, we're going to divide this by this, which produces the small amount of energy. So we'll say 2.754936 expressed to the minus 11 divided by 9.8604 expressed to the minus 13, right? And we get 27.9. So we can see now that the ratio would be 27 to 1, right? So we can make a note here. So we're going to make a note right here, right? So the artificial produces more energy in the ratio of approximately 28 to 1, right? So that would be the ratio when comparing the artificial to that of the natural. So in other words, the natural will produce far less energy than our artificial process. Now, also, the question wanted us to deduce the recommendation that the engineer will give to the investor. So based on our statement right here, right, the engineer would recommend that an artificial process is used because that will produce more energy in the reaction. Right, so that's this question. So let's continue. So now, the next part in the question now says now that radioactive materials emit alpha, beta, and gamma radiation. Table 2 summarizes some of the properties of these types of radiation. Now we want us to copy and complete the table and fill in the missing entries. So we're going to start by talking about the range of our alpha particle in air. Now for the alpha particle, right, so it has a short range, right, short range in air, usually about 5 to 11 centimeters, right? Now, when an alpha particle passes through an electric field, it will be deflected toward the negative plate, right? So the alpha particle, right, it's positive in nature, right, because it's actually a helium nucleus, so it will be deflected toward the positive plate. Now, in terms of in a cloud chamber, right, it will produce some distinct tracts, right? So let us say this is our alpha particle here, right, or our radioactive source. When it gives off alpha particles, right, we're going to observe some very distinct tracks, right, some clear, distinct tracks that look like this, right? So some very clear, distinct tracks, right? Because alpha particles is very heavy, so it will give off these distinct tracks as it is emitted from this radioactive source. So now we can now talk about our beta particle, right? For the beta particle, right, it has a greater range in air, right? It is considered to be a fast-moving electron, right? So its range in air is usually about 500 centimeter to 1000 centimeter, right? That's the range of a beta particle in air. Now, in terms of its behavior in an electric field, a beta particle, as I said before, is a fast-moving electron, so it's negative in nature, so it will be deflected toward, right, in this case, the positive plate, right? While in a cloud chamber, right, because it's an electron, right, an electron is considered to be a very lightweight particle, right? Its behavior in a cloud chamber will be such of the sort that it actually forms some very random tracks that changes direction over time. So the tracks will look something like this, right, in a cloud chamber. So they will actually be quite of a random pattern, change in direction over time. All right, now we can continue. Right, and we're going to now talk about our gamma particle now. The range of a gamma particle, right, so a gamma particle is considered an electromagnetic radiation, so its range is virtually right? Infinite, right? And it's considered as energy, right? So it has an infinite range, and in terms of its behavior in an electric field, because it is energy, right? It doesn't have a charge, it will just pass straight through. So it will pass through undeviated, right? And here they told us about the faint tracks, right? The tracks will look something like this, right? Some very faint tracks in a cloud chamber. All right, so this would be our question completed. So again, Junior Roberts here with realjuniorroberts.com. If there's anything in this video that you wish to get further clarification on, then post it below in comments, and I'll do my best to clear up any misconceptions for you. Like this if it was helpful, and click subscribe on the bell notification so you'll be updated whenever I post new videos like this. Thank you for watching.